All right, good morning. So today's a big day, and I want to make sure. So I made these up a few years ago. For years on the ACS website, you could buy these bumper stickers. They had a bunch of different funny bumper stickers, like Heisenberg may have slept here, because of the Heisenberg uncertainty principle, and it takes all kinds to make the world go round, but it was ALKYNES, all kinds. And then they also had this really funny one that said honk if you pass CHEM. Okay, but it looked like it was hand drawn in paint, and like they didn't use a real font or anything. It was the ugliest bumper sticker, so I made one for Sam here. So if you passed CHEM, you can come up and get one of your bumper stickers, which I think is all of you, since it's a prerequisite. So, we'll go through. I want to see selfies, okay, with your stickers. And I honk if I see it. So. And if for some reason you're not here today, come by and get yours, on the video here. So I'm going to have my folks in India, they're going to be sending me requests with yeah. So we have most of my views outside of Sam are from all over the world on this channel. So it's really fun. Okay, so we'll dive in. Today we're doing a review, so this is going to be nice. You'll get a review, but I'm going to put a few twists on it. We're going to do some things that you probably hadn't thought about in terms of statistics. So we're just covering basic statistics, mean and standard deviation, and talking about measurement systems today. Now, what I've decided to do on the top hat thing, if you're looking at the top hat, you see the quiz is ready to go. We're kind of in this trial period. I'm trying to figure out how best to use Top Hat. I'm really not happy with the way Top Hat uses this pad. Like when I have to write on here, I'm using PowerPoint right now, and I mean, you have really fine detail in terms of my annotations. But the Top Hat's like a crayon, and it's like a crayon between my toes. It's that, it's like that bad. Okay, so I know they're not going to like that. But the annotation is really made in Top Hat, I think, for like underlining things, not writing out standard deviation with subscripts and things like that. So today we're going to be doing a fair bit of math. So I'm going to do today's lecture on PowerPoint, but we'll do the quizzes on Top Hat. So we'll still do those. There's just a couple of questions on Top Hat that we'll do. Jump over to that, and then we have an activity. So this is kind of like high school or maybe even elementary school days. We're going to have a little activity. So everybody likes that. And if your group does really well, I've got stickers. All right. So let's go. So this is this whole idea. Remember, this beginning part of the course is about trust and trust in your data. So you really need to know how to report your data and how to understand the data and to understand the communication that you're conveying when you report data. So since it's about trust, our expert testimony, and you may not be the person that's doing the expert testimony, it may be somebody that's using your results. So it may even be one level removed from you. But that needs to be based upon scientific facts or data, but also reliable principles and methods. And then methods applied reliably to those facts of the case. So you need to have tried and true methods, but then you also need to apply those methods reliably to the data. And then this quality assurance defines what conditions yield reliability. So you're assuring your customer, your external partner, that you're using your methods reliably. And then without statistics, there can't be any quality management or assurance. So we need to look at multiple measurements, average them, look at the standard deviation or the variance, and see what kind of uncertainty is related to your measurements. Now, the quality assurance piece, that's all of the procedures and methods. The quality control piece are the things like the control charts. Okay, so those are things that drive action. The quality assurance is sort of the framework of quality. There's this huge pyramid. It's kind of like an inverted pyramid, and you're at the bottom. All of these organizations and agencies and structures are built to kind of ensure that your job is reliably done. Okay, so it's quite a bit of pressure. You can't just make changes on the fly at the bench. I mean, you have some freedom, but not a lot of freedom to change things at the bench. In fact, there was in industry sometimes it gets so serious they don't want their line level technicians changing anything. And when I was at graduate school in Oregon State, there was a HP printer factory nearby. And they would come and recruit on campus. And one of the recruiters, I was talking with him and said, why don't you recruit the chemists? And he said, we don't want scientists. And I said, what? And he said, we want engineers. And I said, why? That doesn't make any sense to me because, a chemist would understand about the ink and the printer and all of this stuff. And he said, exactly. We want our line technicians to follow procedures, not do science. So I was like, oh, okay, that makes sense. They want someone who's just going to follow that procedure and not do science. But that doesn't mean they don't think. If the procedure has some transposed numbers or something like that, you don't just make up the wrong batch of solutions just because there's a numerical error. You don't follow the procedures in a stupid way. You use your brain as well. So looking at some of these things, you have continuing education up at the top. You have reference materials that you can buy. So how do you know this is cocaine on this FTIR? Well, you have a library sample of cocaine. And so you can run those reference materials. We have those here in the building, but they're in a safe. Okay. We have them up in the forensics on the second floor. Like they have, it's almost like a chain of custody, but it's not evidence. It's the library samples. And so they have, not clandestine. They have controlled substances in their controlled area, and it's under, lock and key because they need those standard materials. There's also quality standards and peer review. The labs will review each other. Then you have laboratory accreditation. So under this professional organization, you have the Association of Lab Directors, Forensic Science Lab Directors. You have proficiency testing. So they'll come in with, you have, say, a GCMS procedure that's set up and you've run controls on it and so on. They can bring you unknowns and test to see if you give them the correct answer. And so you have proficiency testing, you have audits, and then you also have down in the forensic laboratory training and continuing education, and then all of the methods and procedures, the calibration procedures, how you handle your samples, and so on. Now let's dig into the details and start looking at the actual numbers. This is a bit of a review. And so these are the rules associated with significant figures. Because again, if it's about trust, what are you doing when you write a number down in a report? You're communicating with somebody. Okay, and what's interesting is communication. I like to say that significant figures, even though it seems kind of boring, is a really a critical piece of information because it's communicating value. So if I were to take two measurements on a balance, and let's say it was a pretty crude balance, it only measured to 0.1 grams. Okay, so it's a pretty crude balance. So I measure one thing that's let's say I measure it 3 times. I measure 100 grams and it's 100.1. Okay, and then I measure again and it's 100.0, and I measure again and it's 99.9. Okay, so the 3 values hover around 100.0. Okay, and I let's see, let's make 2 of them 100 100.0. Okay, so I'm doing this in my head. And then I'd average those. Okay, so because of that 100.1, it's a third higher than 100.0. And what does my calculator tell me? It tells me the mass is 100.03333333333. And I write that in a report. And so what I've communicated is that I'm now measuring if I've got 10 digits on my calculator, that I've measured out to the 7th decimal place in grams. But my balance only measured to the 1st decimal place in grams. But if I were to write down 7 digits in grams, I'm communicating that I have a balance that weighs out to the nanogram, essentially, like the 100 nanograms. That's an expensive balance. And I'm lying, essentially, just because I was lazy. I wrote out a bunch of significant digits that I don't know anything about. And so that's why we really care about these things, because you can really miscommunicate if you're sloppy with significant figures. Okay, and we're going to let the uncertain digit tell us where to round. And so when we have a standard deviation, that's going to tell us where to round. If we don't have standard deviations, we have to use these significant figure conventions to tell us where to round. And so this is all about where do we round that result. Okay, so let's talk about the rules. And again, the thing that you want to keep is you want to keep all of the certain digits. Like in my measurement, all of those certain digits were the grams. And then the 0.1, that 10th place was the uncertain digit. That was my last digit. That's the one that's going to fluctuate most likely. So leading zeros are not significant. So in this case, we're looking at this number and we see that we only have 2 non-zero digits, and then all of these zeros in front are insignificant. They're not providing any information except where the decimal place is. So the leading zeros are, the only purpose of them is to tell us where the decimal place is. Another way to sort of test this is if you were to write this in scientific notation, it'd be 1.2 times 10 to the minus 3, right? You see your 3 digits in. So 1.2 times 10 to the minus 3. Notice we wouldn't write 0.2 times 10 to the minus 3. Isn't that looks ridiculous, doesn't it? Yeah, so you just know this. You wouldn't keep those zeros in front of the 1. Okay, and so this is not right here. This is right. Okay. Now, if you have a decimal place anywhere in those numbers, those trailing zeros are significant because it's communicating to us that it has measured this out to the 3rd decimal place. So those trailing zeros are significant. And then any zeros in the middle are obviously significant. So we would keep those as well. It's only those leading zeros that are not significant. And then you should never append zeros without justification. Forget what your calculator or Excel gives you. You need to use the significant figure convention to round, or if you know your uncertainty, you would use it to round. Now let's talk about the multiplication and division rules. They retain the least number of significant figures. So if we're looking at this multiplication, I have 11, which has 2 significant figures, times 0.05, which only has 1 significant figure. And so this is telling me that I'm uncertain. I only have 1 digit of certainty, and so that's going to cause me to round this. The result would have been it would have been 0.55. Sorry, let me erase that. Okay, but I only have 1 significant figure, so I pick the largest one, and I round there. All right, so I round this up to 0.6. So in terms of multiplication and division, we calculate the significant figures, and we use the smallest number of those in terms of determining where our uncertainty is. But in subtraction and addition, we retain the least number of decimal places, or I like to say the largest place value. And so my kids are kind of in your generation, and so as they were going through school, I started seeing that that's what their teachers were calling this, was place value. Which have y'all heard the most? Is it just decimal places or place value? decimal places? Okay, so they're both equivalent, but you're looking at this and you're saying, all right, I have 11 minus 0.05. And so this one has 0 decimal places, so the result is going to have 0 decimal places. Now, the way I do this is I'll put a dashed line here like this, and that kind of tells me where I'm going to round the result. Okay, and so I go ahead and do the subtraction. I carry that, borrow that 1 from the 0, and makes it a 9, makes this a 0. Okay, so I've got 10 minus 5 is 5. Okay, then I bring down the 9, that's a 0, and that's a 1. Okay, but then this dashed line tells me where to round, and so it rounds back up to 11. And so I really don't know that I've subtracted anything. That feels weird, but it's true. If I have 11 of something and I'm uncertain whether it's 12 or 10, because my uncertainty is in that first digit, that the ones place, I have no idea if I've lost 0.05. So I know I've got 11 bucks in my pocket. I might have 12, I might have 10. And you're saying, you asked me if I've lost a nickel. I have no idea. It could be 12, I could be 10. You know, my uncertainty is in the single digits, in the ones place. I have no idea about nickels. Okay. And so these are just some examples that I've got. Okay, so let's do a top hat question. Okay. Oh, not yet. Sorry. This is related to a different slide. Let's see. I put this in the wrong spot. Okay. So let's talk about statistical terms, and then we'll do that top hat question. Okay? Sorry for the false alarm. Okay. Okay, so let's go through some of the statistical terms that we'll use for our numbers. Now, we have this difference between terms in terms of taking our measurements of a group or a group of measurements. If we have a small number of measurements, we would call that a sample, and a small number would be observations less than 15. And so we would show that mean with an X bar or an X in angle brackets. This little bar got shifted over here, so this should be like a bar over the X. Okay. And so whenever we're using X bar or X in those angle brackets, that's we're talking about a sample. So we're saying that it's a small number of measurements. If we have an infinite number of measurements, which you didn't know, but infinity is 15, okay, then we can use the mean and show that as the Greek character mu. So if we see a Greek character mu, or if we see a sigma for the standard deviation, we know we have a large number of measurements, more than 15. A lot of times in CHEM, when we were doing our linear regressions, we had 20 or 30 data points, and so we were reporting mu's and sigmas, and that allowed us, when we were doing our confidence intervals, to use the z instead of the t value to come up with our confidence intervals. So let's look at standard deviations. Have you really analyzed this equation? Let's think about what this equation is telling us. And that's one thing I would like for you to have that skill. I worked on it in PChem 1, but I would also like to work on it more in this class. This equation written here is like a paragraph. You remember from your reading comprehension days, whenever you had questions about a reading passage, you would look at the questions first, and then you go back to the passage and kind of dig through the passage. And so that's kind of what I mean, or I want you to do with these kinds of equations, is to dig through that equation and see what's going on. Okay. First of all, the equation requires a mean, and so we've already taken the mean. Okay, and we do that first. Okay. So first calculate the mean, and then you can calculate the standard deviation. So you have to do that first. Now this piece right here, this x of I is each individual data point. And so that's a deviation. Right? Each data point in our data set deviates from the mean. Do you see that? Okay. Now we want to get a number that's going to associate with how good our data is. I mean, if our data is really tight, it's not going to deviate very far from the mean. But if our data is all over the place, we have a poor precision, then there's going to be large deviations. And so we want to try to sum up all of these deviations, but the problem is some of them are going to be negative because our data points are going to be below the mean and others are going to be positive. Well, if we sum those together, then they're going to cancel each other out. So if we add up all the deviations, they're going to all cancel out. The negatives and the positives will cancel because the mean's right in the middle. So we get rid of the negatives by squaring everything. So that's what the square is. So this is the squared deviations to make them all positive, and then we sum those together. So we're adding the squares of the deviations so we get a larger number, and they're all positive. And so then we divide by the number of measurements. But we have this -1 in here. So we'll talk about that in a second. But essentially we're taking the average. Do you see that's an average? You have a bunch of numbers, you add them together, and you divide by the number of numbers that you have. Okay, and that's what we mean by standard, right? We're standard deviation. We're taking those deviations and we're dividing them by the number of measurements, but we squared them, so let's unsquare them. Let's take the square root at the end, okay? So that's why we have a square and a square root. We square them to make them positive, add them all together, divide by the number of measurements, and then we take the square root to get it back down into the level of our measurements, okay? And that's the standard deviation. Now, if the standard deviation, does it go up if I subtract 1 here? This is in the denominator, right? So I'm making the denominator smaller, and so it should go up. So this tends to be larger than this. So the S is larger than the sigma because I'm not subtracting 1 in the sigma, okay? And so if you've got a small number of data points, you calculate S. If you have a large number of data points, you calculate sigma. And the only difference is that -1. Now this n-1 is called the degrees of freedom. And the reason it's not the number of data points is we lost a degree of freedom by taking the mean. So before we calculate the standard deviation, we have to calculate the mean. And you need at least 2 data points to calculate the mean. Okay, so a data point of just a single data point, it is the mean, right? It's just the only measurement. But we calculate 2, you need 2 to calculate the mean. You only really have 1 degree of freedom. I mean, you fix one data point, the other one can move around. And so it's n-1 degrees of freedom to move that mean. You really so you lose 1 degree of freedom whenever you take the mean. And so the standard deviation is what we call a conservative estimate. So let's look at what it happens. There's nothing magic that happens at n equals 14, okay, or n equals 15. I've calculated both the standard deviation and the population and the sample standard deviations and plotted them on here. But you can see as the number of measurements goes up, these get really close to each other. But for small numbers of data points, like 2, 3, 4, 5 measurements, they're quite a bit different. And so let's say we did like 3 measurements here. Let's just pick this one here. I think this is 3 measurements. Our uncertainty is around 5, whereas this one it's around 4. Okay, 5. If 4 is your baseline, then 5 is like 25% higher. Okay, so that's a large difference. And remember what we're going to be using standard deviations to report. When we're reporting data, what does the standard deviation communicate? So here's the discussion part of the class. So if I report to you the data, what is the standard deviation communicating to you?
How confident we are in the measurements.
Or what?
How confident we are in the measurements.
How confident? Okay, so confidence is in there. What other kind of terms that we could use to describe that? Precision, yeah. And there's one more that I'm thinking of. So confidence, precision. This is we get these confused quite often. It's not accuracy, it's the other one. It's precision. But what other term we're trying to communicate with this? Yes? Yeah, uncertainty. That's the word I'm really looking for. But they're all three of these are the correct concept. That the confidence we'll get from how repeatable our measurements are. But yeah, if you have a good precision, then you have a low uncertainty. Okay. And so whenever I'm producing this standard deviation, notice the S is larger than the sigma. And if I have three values, I'm told I should use the S. I mean, yes, I could follow the rules, but doesn't it make sense if I'm reporting to you my data plus or minus my uncertainty, it's a more conservative estimate if I tell you the larger uncertainty versus the smaller, right? I'm saying I'm sure that this is my answer plus or minus this window. I'm going to give you the bigger window. That way I can be more confident. Okay. So that's the conservative estimate to give you the larger window of uncertainty. And so that's why we want to make sure we incorporate that loss of degree of freedom when we have a small number of data points, because it gives us a bigger window of uncertainty, and you're more confident that you're capturing the uncertainty of the process.
So that would be like the difference between, for example, if you're trying to find a 95% to 99, you would pick the 99 because you want to move around.
Yeah, and so then those would be really big limits. And so that would be a very conservative estimate to say, look, I'm giving you my 99% confidence intervals, So that's good. So now we can do the top hat question. Okay, so let me open that question again. So why is the sample standard deviation a more conservative estimate than the population standard deviation? Really two choices. Oh, okay. It looked like our number of students went up. Somebody just logged in. Come on. 10 seconds. Get that last question, that last response. It's not showing up. Okay. All right. So I'll go ahead and end it. Okay. All right, so we're looking for that larger range of uncertainty. That's the conservative estimate. Now, that doesn't mean that in general, a large range of uncertainty is a good thing. We want our uncertainties to be narrow. But if given a choice to report the smaller answer or the larger answer in terms of our uncertainty, we want all of those to be small, but we're going to report the larger one if we have a small number of data points. But we still want we want a small uncertainty. And both of these are going to be small if we have a small uncertainty, and we're going to report the sample standard deviation if we have a small number of data points, because of the two, it's the larger one. Okay, just trying to tiptoe around this. I don't want you to go home thinking that large uncertainties are good, right? Large uncertainties are garbage because you want to be certain with your results, okay? But if you calculate, if you have a small number of data points, you report the S because of those small uncertainties, it's the larger of the two. Okay. All right, very good. All right. Okay, so now let's talk about measurements. We're going to have digital balances and things with needles. Things with needles are less common, but they're still out there. And so every measurement, even a single measurement, has some uncertainty. And it's acceptable to estimate one digit beyond the tick marks on an analog readout. So on an analog readout, we're looking at this here. This this needle is not pointing at 125 or 126. It's going in between. And so you could report that as 125.5. And so that's half of that tick mark. So that's the way you're supposed to measure. And so are you sure? Where's your certain digits and your uncertain? This 125 is certain if the needle's not moving. And so those are certain. And then this is the uncertain digit. And the same here. We have, again, 4 significant digits. The number of significant digits is all the certain digits plus the one uncertain digit. Okay. And on this digital balance, we're looking at this, and it keeps going back and forth. It just won't stop, but it is constantly going between 4 and 5, 4 and 5. If it did this for a while, you might even be able to say 125.4, and then it keeps swapping. So you could write that down. Okay. Because it never goes below 0.4. Okay. But that's less common that you would see that. A lot of times it just is climbing. Most of the balances, you've got something that's absorbing water and it's just climbing and it won't stop. Okay. And so let's talk about our measurement system evaluations. Now, most of the time when you buy an instrument, the box or the literature will tell you, like our 4-place balances, our analytical balances, they say that they are repeatable to 0.0002 grams. And so we see that a lot of the times. And so that's going to be an estimate of the repeatability of that balance. But we want to consistently calibrate our instruments. And a lot of times these things work with balances. Mass is typically the foundation. And so we'll calibrate our balances, and we know that our balances are accurate. And then we'll use those balances to calibrate our pipettes. And so you may say, golly, how, to measure the mass of a 10 microliter drop, okay, do we really do that? Yes, we really do that. So we got the density of water, we know the temperature, we put those drops on that pan, and you're good at Excel, right? So you don't put a drop on a pan and then take the pan off and put a new pan on and tear it and put a single drop on there. You just go up 10, 20 drops and you measure the slope. And so every increment is supposed to be 10 microliters, and you're looking at the growth in mass. And so you got mass per microliter, and you can see if that pipette is delivering what it says it's delivering. And over 20 measurements, you'll see if that slope is slightly less than it needs to be, and you get a really good. Not only that, with your Excel skills in your ANOVA analysis and regressions, you can get uncertainties. So you can say that this pipette delivers, X microliters plus or minus. And so you can get from that ANOVA analysis your uncertainties in your pipettes. And so those pipettes then are used to calibrate instruments. And then those calibrated instruments will validate your methods. So every one of those steps affects the ones below it. So it's pretty interesting that even our large instruments, GCMS, still stands on the shoulders of our lowly balance. Okay. And so when we're looking at the balance and its uncertainty and how it produces uncertainty in our volumetrics and our volumetrics into our calibrations, propagation of uncertainty is a critical skill. We're going to go through that again on Thursday. We'll go through that lecture and we'll show again how to propagate the uncertainty from a calibration curve. And so we'll get really good at propagating uncertainty in this course. So let's do this measurement exercise. Okay, so I'm going to just go, since there's 3 rows, I'm going to have y'all work in groups. You don't have to move your desks or anything. each little desk pair will, let's do that. Everybody gets their own little ruler, and each desk pair will get this number. So you're going to measure that circle. Yes. And don't talk to each other on this one, okay? Because this is that's part of it. Now, in your little desk teams, you guys can talk. So pairs can talk. But don't talk like down the whole row, and don't talk to the row in front of you or behind you. So pretend that you are not even in the same city as the row in front of you or the row behind you. And the only instructions you have are on the screen. Use the measurement tool to measure the circle. That's what you're doing. Okay, so let's go.
Can we do like one for each?
Yeah, each one. And this row, if y'all put row 1 on your little post-it note. And you put row 3 on So you put row 3 on okay, there you go. Okay. You're measuring. You measure the circle and you measure this on there. Here. Yeah, right. So measure the circle and measure the direction. Row 3 pictures and stuff like that. But all the pictures they were using were so fast. I was like, I guess the side, like the first row, the last row, and also like we're on and maybe you can also This still has I gotta look at this view. Okay, good. All right. Okay, y'all ready? All right, so row 1 here, group 1. So our measurements are, let's see, 10.2, 10.2, 10.2, 10.15, 10.1, 3.95, 10.2, 10.15. Okay. And they put this when they put a slash here. Now, I know. Yeah. And so I just wanted to show like that number really stands out. And so then you'd have to investigate. Let's say you weren't able to inquire of the person that made the measurement, right? You know, you did write your unit, so that's very good. But like if you were just looking at the data in Excel, because a lot of times in Excel you just have numbers. Yeah. And so you would say, whoa, what's that? But then if you maybe did a conversion, you'll say, okay, that's the same. It's the same number. Okay, so you could check that. And so so all of these, it seems like all of row 1 use centimeters, and you did centimeters and inches. So very good. And so these are all centimeters. Definitely we could look at that just visually. This was the silliest thing. I took a statistics course in industry. It was a Six Sigma, quality assurance type thing. It was applied statistics. And they said the very first thing you do is an ANOG. And I was like, ANOG, it was the dumbest acronym I've ever heard. It's called Analysis of Good. But that's what the instructor called it. I thought of eggnog when he said it, but yeah, you do an eggnog. Analysis of good is just to see if the data is good, right? And yeah, this looks pretty good, right? Most everything's centered around 10.2. We have a 10.15. So yeah, so it looks like the circle's 10.2 centimeters. Now, some people wrote diameter on here, so it looks like this is equal to the diameter. Okay, now this said measure the circle. It wasn't specific. And so now you see what's difficult about a non-specific procedure, right? So what does that mean to measure, right? So row 1, even though I told you not to talk to each other, you all kind of decided that diameter was the thing that you were looking for. Okay, so that's cool. Now row 2. Okay, so here we have same circles. Okay, 8.3. Okay, we have a 3.6 inches or 8.35 centimeters. So these are centimeters. 8.3, 8.3, 8.3. Interesting. Then we have a bunch. There was like a 8.42, 8.43, 8.44, 8.41, 8.40. This was a whole group, so they measured it 5 times. So I would say 5. Let's see. Yeah, 5 replicates. So they measured the same circle with the same device 5 times. Okay. Duplicates would be taking something from the very beginning, so like a brand new circle and a brand new measurement device. But when you measure the same thing with the same instrument, that's a replicate. And then they had the radius, so half that, 4.2. But again, if you didn't know that these were labeled diameter and radius, the 4.2 would really stand out, or the 3.6 would really stand out. So you can really see why units are important, okay? And what you're measuring is important. So this is radius, and these are diameters. What about number of measurements? So here we have 1, 2, 3, 4, 5, 6, 7. So n equals 7. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n equals 10. Okay, let's look at group 3.
I have a question.
Yes.
So you said replicate was the same thing with the same instrument.
Mm-hmm.
So, and duplicate would be same thing but different?
Yeah, it's kind of hard to determine the difference between those two words with this simple exercise, but think about like a GC. If you take your sample, the same concentration, and you prepare vials from that sample, that's a duplicate. So you're taking the sample, you're splitting it into 2 or 3 or 4, and preparing samples from the beginning all the way up through the vial that goes in the GC. A replicate would be the same vial measured again. So that vial is prepared, goes to the GC, and you run it twice. That would be a replicate. So you're just seeing how the actual GC signal varies, whereas a duplicate, you're actually seeing how your whole procedure varies. So you're capturing different parts of the uncertainty. So replicates give you some information. They're more focused on the instrument. And duplicates give you information about your procedure. Yeah. Group 3, so we have 5.4 centimeters. That's diameter. And so 5.3. 5.4. There's one. This is pretty cool. They reported everything: the radius, diameter, area, and circumference. That's awesome. Yeah. Sad thing, no units. So I have numbers there, but yeah. So diameter is 5.3. But yeah, there's 27, 5.3, 22, 17, or 2.7. Yeah. But so anyway, it's great though. It's like a comprehensive view, but I have to guess on the numbers, the digits, or I know the units. I mean, and so then here's a 2.1 inches. So inches, okay, and circumference 6.6 inches. So we have inches here. We have centimeters there. 1, 2, 3, 4, 5. I'm assuming that's a diameter. N equals 5. Okay. So look, we've got 7, 10, 5, and we've got the same circles, but we've got dramatically different numbers for those. So why? The instruments are different. So we have pretty good uncertainty. Our precision is good. but our instruments are different. Okay, we could pretend that one of those instruments is calibrated and the other two are not calibrated. So one of those instruments may be accurate and the other two dramatically biased. Okay, and so you can still have really good precision and be completely off in terms of accuracy. So I don't know which at this point, which of those instruments is the true or closer to a calibrated value. But you can see how even though, multiple people measuring the thing, if everybody's using an instrument that's drifted off its calibration, then you can have great precision, but just be totally inaccurate. Okay. Now, let's say that we have, this is the Department of Public Safety, and you have this row as a different crime lab, okay? And we send out these samples of circles and we get back our results and we're like, oh my gosh, lab 1 gives us an answer of 10, lab 2 gives us an answer of 8.3, and lab 3 gives us an answer of 5.4. We've got a problem, don't we? Each lab, it's lab dependent, and maybe those labs are using calibrated instruments, but their procedures are different. So it may not be something as simple as an instrument calibration. Each lab may be statistically significantly different than the other labs because their procedures, maybe their dilutions are different. Maybe they have a different way of handling the samples. Okay, maybe one's using standard additions and the other one's using external standards, and then third one's using internal standards. So there's different ways to calibrate your instruments, and which is the right answer? Right? So that's a real tricky question. Can we get the sort of group precision, though, of the whole state? How would we do that? Yeah, so for getting the uncertainty for the whole state, like let's say we're all reporting in centimeters, so we all have a compatible reporting unit, okay? We could calculate the standard deviation for each lab, each row. Okay, so let's do that. Does anybody know how to use the statistical function on your calculator? Have you ever used those statistical tools? So I've got it on mine. There's let's see, I got to find the right button. Down here, there's a little sigma plus, okay? And there's the sigma minus, but we're looking for the sigma plus button, okay? And so your calculator will calculate standard deviations almost always if it's a scientific calculator, but you got to know how to use that, okay? And so I'm gonna kind of show it on the camera here. So I'm gonna do the group 3 because it's only got 5 values, okay? So we'll start with that one. So. Okay, so I have nothing entered into my calculator yet. I'm going to type in the 5.4, and I'm going to hit that sigma plus button right there. Okay, sigma plus. And down here in the bottom corner of my screen, it says n equals 1. And so if you have what does it look like on yours?
I'm not sure how.
So that's a TI 83, yeah, or 84. Let me see. If you know, speak up. You're looking for the stats. Okay. So can you do group 1? Okay. And then once you figure out, give us a tutorial. Maybe you can make a video or something. Okay. And so I'm going to do the next one, 5.3. And I'm going to hit that little sigma plus button, and it says n equals 2 on my screen. And then 5.4 again. So n equals 3. 5.3. Okay. And then the 2.1, I'm not going to put that one in there because that's in inches. So let's see, it'd be 2.1 times 2.54. 2.1 enter 2.54 times. So that converted it over to centimeters. So it's 5.334. Okay, I'm going to hit plus. So now I have 5 data points. So there's my 5 data points. I put them into the little stack of data, and then I can come down here and hit function, and there's a sigma there. So function sigma, and it tells me the standard deviation. So it's telling me 0.05 is my uncertainty. Okay. Did it work? Okay, so this one right here gave me a 0.05 centimeter standard deviation. On which one? What?
I have a TI 83.
Yeah, so did you figure it out? Okay, so tell us the steps.
So you go to stats, and then in the first tab it says number 1 edit. You put your data points there under like L1 or L2 or whatever it is. And then you go second stats, and then on the top it says names, ops, or math. Go to math, and then you click 7, which is your standard deviation. 7. And then you have to do second 1 or second 2, depending on what L you use, line. That'll be where your data points will be at. So you do your standard deviation, second 1. Let's say you guys use flag 1, and then you enter, and then it'll give you your standard deviation.
Okay. Okay, so did you calculate it for group 1?
Yeah.
Okay. So this whole thing was S equals what?
0.04. I got 3 9, so I'm gonna round to 4.
Okay. 0.04. Okay.
And I got she put in the group 3 data point, and we got that.
Okay, good. Now, in this one, I want to go all the way. I want to use all of these guys here. Okay. So I want to use all 10 data points for that. Is somebody entering that one, or should I start? Okay. 0.06. Okay, so even though our labs, so Texas DPS is looking at this and going, okay, we got 3 crime labs here. They're definitely using different procedures, but how is their uncertainty related to their results? Lab 1 has a 0.04 centimeters, Lab 2 has 0.06, and Lab 3 has 0.05. Okay, can we get a statewide standard deviation? Right? If Washington calls us and says, all right, Texas, what's your statewide uncertainty in your results? And we have 3 labs. How do we merge these 3? That's what the pooled standard deviation is for. You may have heard that pooled standard deviation. If you look down here, this is just a weighted average of the variances. So the variances are S squared. So go ahead, let's square these numbers. S squared is equal to, oh, this is S, sorry. Yeah, and it's just that, it's just that number squared. So S squared, if someone would square all of these and tell me those. I should be able to do it in my head. 4 times 4 is 16, but let's see. Yeah, 0016. Okay, any arguments with that? If I make a mistake, tell me. I really get angry when I make a mistake and you just sit there and let it go. Okay, because it's just not right. Don't do that. Okay, so now down here, if you notice, what is this pooled standard deviation? It looks complicated, but it's not. This is the degrees of freedom for group 1. And it's divided by all the degrees of freedom in the whole room, right? Or in the state, right? We're talking about. So group 1, so we have our S pooled is equal to the square root. And then we've got row 1, so S squared for row 1 is 0.0016 times n minus 1, right? We have n equals 7, so 7 minus 1, so it's going to be 6 times 6 plus 0.036. So n equals 10, so that's going to be times 9 plus 0.0025. And in this case, we had 5 measurements, so it's going to be times 4. So do you see what this is doing? It's putting more weight on group 2 because group 2 has more measurements. So we're more confident that group 2's, we want, the uncertainty for 10 measurements was 0.06. And so we're going to weight that one higher than the uncertainty in group 3, which only had 5 measurements. Okay. And so then we divide by the sum of all of those numbers. Divide by 6 plus 9 plus 4. And so that's how you calculate the pooled standard deviation. Yes?
Sorry, would it not be the n
It's n1 plus n2. And why is this minus 2? It's the n1 minus 1 and n2 minus 1. And so we have the degrees of freedom in all of those. So what are you asking?
Would it not be 7 plus 10 plus 5 minus 2?
Well, this minus 2 is only there. It's only 2 because there's 2 groups.
Okay.
It'd be minus 3 if there were 3 groups.
Okay.
And so since there's 3 groups, it'll be minus 3 where you could take 1 from each. So it's just the sum of the degrees of freedom is what it is. Yeah. Yeah. So
I still think the n values are wrong.
the n values are wrong?
It should be 7, 10, and 5, not 6, 9, and 4.
No, but it's minus 3. So now
Minus
you're
three.
one off.
Oh, you took one off.
Oh, so it doesn't matter at the end.
Yeah. So what it is, so it'd be 7 plus 10 plus 5 minus 1 minus 1 minus 1. Yeah. That's okay. No, that's why we're doing this, because the equation looks weird. And it's really just the degrees of freedom are the weighted average of each degree of freedom. Yeah, no problem. And so then we do all that. So what is our S pooled for the state of Texas here? Did somebody do this already, hopefully?
I got 0.05, but I did it on my phone, so.
Yeah, but it, 0.05. Okay. And here's the 0.06 is our largest, most certain value, but then we pull it down for this one and pull it down. So it makes sense that we pull it down from 6 to get to 5. So do we have a confirmation of that number? Okay. Okay, yeah. We'll just keep one digit of uncertainty. And so I didn't put the units in here. So these units in here are centimeters squared, right? Because we squared these. I just want to make sure you see that the units work out. And so we have all these centimeters squared. The numbers of data points are just numbers. They have no units. They're also exact numbers, meaning they're counting numbers, and they don't limit our significant figures. So when you take an average of something, that doesn't change the sig figs because you're dividing by the count, and a count has an infinite number of sig figs. So it's just, if you're thinking, wow, I divided by a number with one significant figure, that should ruin my precision. That's not the way averages work. So you're using counting numbers, they don't limit your precision. Okay, same thing for the pooled standard deviation. Anytime you're taking averages, those are all unitless numbers, they're exact numbers. But you have the centimeter squared. Once you take the square root, we get back to centimeters. So their standard deviation has the same unit. So this would be the standard deviation for the whole state. So we would report the average value of all of these things. But it would be a problem because group 1 has a different average than group 2, which has a different average than group 3. So we couldn't really get a consensus view on the size of the circle, but we could realize that our precision is very good. statewide. Okay, and we're just using different procedures in their labs. Okay, so that's a sort of a measurement system evaluation. We're definitely seeing that it matters which lab we send it to. Okay, in terms of accuracy, or if we, send the standards and the unknowns to a particular lab, we can't let lab 1 analyze the standards and pass their calibration on to lab 2 and have them run the samples. Okay, that won't work because they give different answers. Okay, but if we stay within a particular lab, then we'll get the answer that that lab produces, and we'll have good precision in any lab that we use. Next time, we're going to start looking at some of the other precision values that we can use and ways of analyzing the different statistics. So we'll go through all of these values. We'll do propagation of uncertainty, and then we'll start looking at things like variance. We used variance today, which is just standard deviation squared. We'll look at skewness and kurtosis. We'll look at some of these normality tests and quartiles and confidence intervals. So we'll look at these statistical terms. This is using a nice package called Minitab. You should have access to it through this campus software. So if you're in a computer lab or if you are working on a campus managed machine, you should be able to install Minitab. And this is what we call the descriptive statistics or graphical summary of statistics. So what you do in Excel is very tedious, typing in all of the little equations, and we'll do an exercise where you type in all those equations. But in real life, you use a program like Minitab. You just have a column of data and say, tell me everything about that data. You just select that column, and this is what you get. You get all of this information, the mean, the standard deviation, and everything, and it makes life so much easier. Okay, so we'll learn a little bit about how to use Minitab too in this course. So it's nice to kind of graduate from Excel and actually use the tools that professionals are going to use on a regular basis. All right, y'all have a great day. Oh, great question. Yes. I need to go on and make sure everybody has yeses in their columns. And so once you get a yes, you start collecting data. You can start collecting now, but in case there's a problem, don't commit too much into it just yet. Yes.
When do you want us to have this control chart idea changed?
You should have you already entered something in?
Not yet.
Okay, so go ahead and make your decision and get that entered in today. You can keep the rulers. Yeah, and so get those things in, those ideas in today if you can. Yeah, sure.